A factory produces boxes of breakfast cereal with the labelled weight of 1 kilogram. Let mu denote the population mean and sigma denote the population standard deviation of the weights of the boxes. The factory sets the packaging process to a mean weight mu is 1.01, with a standard deviation sigma is 0.05. To maintain quality, a random sample of 400 boxes is taken each day and weighed. Let X bar denote the sample mean weight. We want to state the distribution for X bar and its parameters. Well, first of all, we should note that n is equal to 400. Being greater than our usual measure of 30, we can say that X bar is going to be a normal mu and sigma X bar squared. So what about sigma X bar? That is going to be the 0.05 over the square root of 400, which is 0.0025. And therefore X bar is going to be a normal 1.01 and 0.0025 squared. In part B, we want to determine the probability that the sample mean is more than 5 grams above the labelled weight. Now note, we've put this in kilograms. So what we're after here is the probability that X bar is more than 1.005. That's the 5 grams converted into kilograms there. And we should be able to do that straight away on the calculator. So if we go interactive, and we want continuous normal CDF, our lower is going to be 1.005. The upper we can use infinity, or you could use a really large number, many standard deviations up, and that will work just as well. Sigma is 0.0025. And the mean is 1.01. And our answer there is 0.9772. So 0.9772. Okay, continuing. The sample mean on a particular day is X bar is 1.05 kilograms, while the sample standard deviation is X is 50 grams. Determine a 95% confidence interval correct to 0.001 kilograms for the population mean weight based on this sample. Note that 50 grams is exactly the same as 0.05 kilograms, and therefore we're going to use the same value as we did above. So the 95% CI is going to be 1.05 take away 1.959964, this value being the Z95 value, we'll see that in a moment, times 0.0025. That 0.025 being the same 0.025 from up here, because the 50 grams was the same as the 0.05 kilograms. And we'll also have at the other end, or perhaps we should write here, is less than mu, which is less than, and then it will be the same thing with a plus, like so. And of course you can calculate that, or you could just use the E activity for this. There is an E activity, we just need to be in the right thing, so we're just going to open up our spec 3.4. Yes, I'm sure. And so z-score for CI, we don't actually need that right at this second, but that does tell you where you can get the 95 if your confidence interval is, I think we put in 0.95. I'm not sure about that, but we'll try it. And yeah, we can see that's the 1.95 figure that we had before, but we don't actually need that because we have got an activity that will do the trick for us, which is this one here, confidence interval for the mean. And all we need to do is go up here and fill in the appropriate values. So we just need to change the mean there to 1.05. The standard deviation. Now with the standard deviation, we need to put in the standard deviation before it was altered. So that is the 0.05, because the very next parameter is the n value. And we know that our sample was 400. And we're doing 0.95, so that should actually do it if we just go there and we just execute. And that gives us 1.045 and 1.055. So that is the correct value. So 1.045 and 1.055. So what do we have next? Anja, a quality control officer, wants a 95% confidence interval based on the sample size of 100 with the width of no more than 0.1. So if the width is 0.01, that's the entire width, then the standard error is 0.1 she wants. It's half of that, which is 0.05. And that is our error, 0.05. And so we can use to find the maximum standard deviation what we want. So we've got the z-score for CI. We know it's 95%, and we already went in and did that earlier on. And the sample n for CI is the one we want. Now, we want to set that to 100. And we've got the Z value correct in there. The E value is 0.05. And we're going for the standard deviation. And that gives us 0.2551. If you want to show some working, we have the formula just here that n is equal to z sigma over e squared, and just substitute your values in just there. Over the next 50 days, Ben, who is a data collection agent, takes random samples of size 100 each day, and a 95% confidence interval is calculated for each sample. 10 of these 50 intervals, 20% of the intervals, so 20% is 10 out of 50, have a lower bound that is less than 1 kilogram. Ben claims that this indicates the mean weight of packaging is set too low. Is Ben correct? Justify your response. The 2 marks, one for getting it right and one for justifying it. So the first thing I would say is there's a natural variation in the data. A 95% confidence interval means that in the long run, 95% of the confidence intervals will contain the true mean. There's no guarantee of those confidence intervals being above a certain value, so he's just incorrect.